This is part second of linear ordinary differential equation with variable coefficients, and in this video we are going to discuss Legendre's linear differential equation. So consider an example. So if we observe this, coefficient of each derivative is containing the same power of the linear factor 5 plus 6x as of the order of the derivative. For example, this is the first term. What is the order of this derivative? 3. And along with that, what is the power of this factor? That is also 3. Similarly here, this is our second term. And what is the order of this derivative? That is 2. And along with that, we have 5 plus 6x power 2. Similarly, this is a third term. Here, what is the order of this derivative? 1. Okay. And along with that, we are having 5 plus 6x means same factor with power 1. Okay, so this is a special thing about the Legendre's linear differential equation, that coefficient of each derivative will have one linear factor along with the same power as of the order of the derivative, and this factor will be same. Okay, like 5 plus 6x is same for all these three derivatives, right? And one more thing, along with this you may have some constants also. For example, here we have 7, here we have minus 6. Okay, you may have some constant along with these factors. And on the right hand side, you will have a function of independent variable. Okay, so here what is the independent variable in this example? X. So on the right hand side, we are having the function of x only. Fine. So the journal form of Legendre's linear differential equation is this. Okay, so here what is the factor? We have a plus bx. Okay, and this factor is having the same power as of the order of the derivatives, right? And this a1, an minus 1, an, all these are constants. And this capital X is what? This capital X is a function of independent variable, and that variable is x. So our independent variable is x. So capital X is a function of x only, small x only. Okay. Now let's understand how to solve Legendre's linear differential equation. So as such, we are not having any method to solve this. So what we will do, we will make some substitutions, and after doing that, our Legendre's linear differential equation will convert to the higher order linear differential equation with constant coefficients. And then we'll apply that same method of complementary solution and particular integral. Now let's see what are the steps. So first step is put a plus bx equals to e power z. And after taking log, what we will get? Z is equals to log base e a plus bx. Now what is the second step? Second step would be wherever you have a plus bx into dy over dx, put that b, small b, capital D, y. Okay, what is capital D? Capital D is derivative with respect to z. And what is this b? This b is the coefficient of x. Okay. Now what is the third step is wherever you have a plus bx whole square d square y over dx square, put b square d minus 1 y. Similarly, fourth step is if you have a plus bx cube d cube y over dx cube, put that b cube d minus 1 d minus 2 y. And further, for higher order also we will proceed in the same way. Okay, now before doing any question, let me explain you how we are getting this thing. So see, initially y is a function of x. And when we make this substitution that x is equals to e power z, then x become the function of z. Now, if I ask you to differentiate y with respect to z, now y is what? Y is direct function of x, but y is the composite function of z, because y is function of x and x is further a function of z. Okay, so y become the composite function of z. So what we will get by using the concept of composite function, we'll get dy over dz equals to dy over dx into dx over dz. Now from where we'll get this value dx over dz. Now from this substitution, because we are taking a plus bx equals to e power z, what will be the value of x? X will be e power z minus a over b. So if I differentiate this with respect to z, what we will get? Dx over dz will be e power z over b. Now what is e power z? E power z was a plus bx. So that means dx over dz is what? That is a plus bx over b. Okay, now substitute this value here. So what we are going to get? So your dy over dz will be equals to dy over dx a plus bx over b. Now take this b on other side here. So what we will get? B dy over dz equals to dx over dy over dx a plus bx. Okay. Now see, this is something which we are assuming as capital D, right? So what we are getting? So b into capital D y, this is capital D, right? Y equals to a plus bx dy over dx. So this is how we are getting this second thing. Alright, fine. So this is how you will get this step 3 and step 4 also. We are not going into this. So now let's understand how to solve the questions. Now this is our first question. So this is 1 plus 2x whole square d square y over dx square minus 6 1 plus 2x dy over dx plus 16y equals to 8 1 plus 2x whole square. So here what is our a plus bx? 1 plus 2x. So just apply step number 1. So we will put 1 plus 2x equals to e power z. Okay. And from here z will be equals to log 1 plus 2x. This is understood that base is e. Okay. So I'm not going to write e again. Okay. Though this is understood. So now next is second step. Wherever we have 1 plus 2x dy over dx, what we will do, we will put this derivative with respect to z along with b. What is my b here? B is the number constant which you have along with x. So here what is the b? B is 2. So 2 capital D and here y. Okay. And what is capital D? Capital D is derivative with respect to z. Now because we have second order derivative also. So 1 plus 2x whole square d square y over dx square will be equals to 2 square d minus 1 y. Okay. Just make these substitutions here in this equation. So what we will get? So this is what? This is d minus 1 into this 4. Okay. Y minus 6. What is this? This is 2 dy. Okay. 2 dy plus 16y. Now please don't forget to change this. Okay. So what was your 1 plus 2x? 1 plus 2x e power z. So this is 8 e power z, and because we are having square of this, so 2. Alright. Now after simplification, what we will get? We'll get this thing. Okay. Now here 4d square minus 16d plus 16 y equal to 8e 2z. Please keep this thing in your mind that after making these substitutions, your independent variable will be changed and your complete equation will be in the form of y and z only. X will not be there, okay, because x has been substituted in the form of z now. Alright, don't forget to change the right hand side as well. Alright, now this is a higher order linear differential equation with constant coefficient. Can I take 4 common? So this will be d square minus 4d plus 4y equal to 8 e power 2z. Now this 4 will be cancelled. Here you will get 2. So what is the updated equation? This is d square minus 4d plus 4y 2 e power 2z. So this is our higher order linear differential equation with constant coefficient. So now let's see how to solve this. Now we have this equation. We'll solve it by calculating the complementary solution and particular integral, which we have already covered in the previous videos. So what is the auxiliary equation? Auxiliary equation is d square minus 4d plus 4 equals to 0. Now what will be the roots? So roots will be, so this will be d minus 2 whole square equals to 0. So roots will be 2 comma 2. So these are real and repeated roots. So what will be the complementary solution? So complementary solution is C1 plus C2 Z. Now see, keep this thing in your mind. This time your independent variable is not x. Your independent variable is z now. So here we'll write z e power 2z. Okay, this is our complementary solution. Now come to the particular integral. So particular integral will be equals to 1 over f of d and capital X. This is our capital X, okay, and this is our f of d. So what we'll get? D square minus 4d plus 4 2 e power 2z. Now this 2 is what? This 2 is constant. So what we can do? We can just shift this on the left hand side. Okay. If you are not aware of the particular integral and complementary solution, you can check the previous videos. I'll put the link in the description box. Alright. So now here we get this thing. So because we have e power 2z, so we'll apply rule number 1. And what was rule number 1? If you have e power a x type of function here, then in order to get the particular integral, put d is equals to a. Now what is my a? A is 2 here, right? So put 2 here, what you'll get? 1 over 2 square minus 4 into 2 plus 4. So what we are getting? So we are getting 8 minus 8. So we are actually getting 1 by 0. Okay, so whenever we get 0 in the denominator, that is the case of failure. So in case of failure, what we used to do, we multiply one x from the, sorry, one independent variable from the left hand side, okay, from here, from this side, and we'll differentiate f of d, okay. So we'll do this thing now, okay. So this is my f of d, okay. We'll multiply one z from this side, okay. And what is the derivative of this with respect to d? That is 2d, okay, minus 4 e power 2z. Now again put d is equals to 2. So if again I put d is equals to 2, what we are going to get? 2 into 2 minus 4. So again we are getting 0. Okay, 0 in the denominator. So again we'll apply the same method. Okay, so as we are getting 1 over 0. Okay, so this is again a case of failure. Alright, so what we need to do, again we will multiply 1z from this side, okay, from this side, and we'll differentiate this f of d again. So what you are going to get? So this will be 2z as such, 1z we are again multiplying from the left hand side. And what is the derivative of 2d minus 4? That will be 2 e power 2z. Okay, so what we are getting? This 2 will be cancelled. So z square e power 2z. So this is the final answer for particular integral. Why so? Because now d operator has been vanished. So that's why this is our final answer. So what would be the complete solution? So complete solution is y is equals to complementary solution plus particular integral. What is our complementary solution? That was c1 plus c2 z e power 2z. Okay, and what is the particular integral? That is z square e power 2z. So this is our complete solution, but this is not the final solution because question was in the form of x and y. So we have to write the answer in the form of x and y. So z should not be there. We have substituted x is equals to e power z just for the sake of simplicity, so that we can get the higher order with constant coefficient and we can solve it, right? So now we have to back substitute the value of z. All right. Now because our z was what? Log 1 plus 2x. So wherever you have z, put this value. So what we are going to get? So in this solution, y will be equals to c1 plus c2. Now what is our z? Z is 1 plus, sorry, log 1 plus 2x. Okay. Now e power 2z. Can I write this thing as e power z whole square? So e power z was what? E power z was 1 plus 2x, right? So just substitute this value. So here you will get 1 plus 2x whole square. Okay. Now next come to this. So what is z square? Z is this one. So you will get plus log 1 plus 2x whole square. Alright. Plus into Now what is e power 2z? Again, this can be written as e power z whole square. So this will be 1 plus 2x whole square. So this is a final answer for the given Legendre's linear differential equation. Okay. Now let's do the next question. So next question is this. Here we have 3x plus 2 whole square d square y over dx square, 3 into 3x plus 2 dy over dx plus 36y equals to 3x square plus 4x plus 1. So this is our Legendre's linear differential equation. So what we will do, we'll put 3x plus 2 as e power z. And what will be the value of x? X will be e power z minus 2 over 3. Okay. And now next is, if you take log on both sides, your z will be log 3x plus 2. Okay. Now further put 3x plus 2 into dy over dx equals to, now what is my b here? B is the coefficient of x. So b is 3 now. Okay. So this will be 3 capital dy. And what is capital D? That is the derivative with respect to z. Similarly, 3x plus 2 whole square d square y over dx square, this will be equals to 3 square d minus 1 y. Okay. And capital D is same as this. This is the derivative with respect to z. Now make these substitutions and let's check what we are getting. So here this is equals to what? 9d minus 1 y. So 9d minus 1 y. Now what is this? This 3 as such. Okay. And what is this? This thing is equals to what? This is equals to 3 dy. Okay. 3 capital D y plus 36y. Okay. Now come to the right hand side. 3x square. What is the value of x? X is this. Put this value. So what we are going to get? 3 e power z minus 2 over 3 whole square plus 4 e power z minus 2 by 3 and plus 1. Okay. Now just simplify this. What we will get? So 9d square minus 9d plus 9d, okay, and plus 36 y. On the other side, what we are going to get? So here you'll get 3 into a plus b whole square. So here you'll get e power 2z, okay, plus 4 minus 4 e power z. All right, and over you'll get 9. Here what you'll get plus 4 e power z minus 8 over 3 plus 1. Now this 3 and this 3 will be cancelled. So after calculating the things and simplification, you'll get, if I cancel this, what we will get? This. So here this 4 e power z will be cancelled with this. Okay. And this is 7. Okay. 4 plus 3, 7 minus 8. So what we are going to get? So from here you can take 9 common. So you'll get d square plus 4. Okay. And here you will get e power 2z minus 1 by 3. Okay. So next what we are going to get? So now if you take this 9 on other side, you will get d square plus 4y equals to e power 2z minus 1 by 27. Alright. Now this is higher order linear differential equation with constant coefficients. So what is the auxiliary equation? The auxiliary equation is d square plus 4 equals to 0. So what are the roots? Roots will be plus minus 2 iota. So according to this, what will be the complementary solution? So complementary solution will be e power real part. What is the real part of this? Can I write this thing as 0 plus minus iota into 2, right? So real part is 0 into independent variable. Now our independent variable is z, not x. Okay, so we write z here. C1 means first constant. Cos, what is the imaginary part? That is 2. 2 into independent variable z plus C2 sine, again independent, imaginary part, that is 2 into z. So this is our complementary solution. Okay, e power 0 is 1. Okay, so complementary solution will be C1 cos 2z plus C2 sine 2z. Okay. Now what will be the particular integral? So particular integral will be 1 over f of d. What is f of d? F of d is d square plus 4. Okay. And on other side what we have? Our capital X is e power 2z minus 1 by 27. Alright. So how we can write this? So we'll write it like this. 1 over 27 will take on other side. So this is 1 over d square plus 4 e power 2z minus 1. Okay, now split this into two parts. So you'll get 1 by 27 as such. 1 over d square plus 4 e power 2z and minus 1 over d square plus 4 into 1. Okay, now because for constant we don't have any rules as such for particular integral, so can I write this thing as e power 0z, because e power 0z is ultimately 1. Okay, now apply rule number 1 for particular integral, and that what is that rule? That wherever you have d, put az. Okay, so this is our rule number 1. For this case, what is your d? D is 2. Okay. Let me change it here where our independent variable is z. So whatever the coefficient of z you have, we'll put that at in the place of d. So here put d is equals to 2. And what is the coefficient of z here? That is 0. So d is equals to 0. Put d is equals to 0 here. So what we are going to get? 1 by 27 as such. So here you will get 2 square plus 4 e power 2z, and here what you are going to get, we'll put 0, d is equals to 0, so 0 square plus 4. Okay, so what we have? So we have 1 by 27, 1 by, here what we have, 8, 2 square plus 4, 8 e power 2z minus 1 by 4. Okay, so now d has been vanished. So this is the final answer for particular integral. So what is the complete solution? So complete solution is complementary solution plus particular integral. What is the complementary solution? This is the complementary solution. Now what is the particular integral? This is the particular integral. Okay, so y will be equals to c1 cos 2z plus c2 sine 2z. Okay, and what is the particular integral? That is 1 by 27, 1 by 8 e power 2z minus 1 by 4. Now is it a final answer? No, this is not a final answer because question was in the form of x and y, so answer has to be in the form of x and y. Okay, so as e power z was 3x plus 2, so z will be log 3x plus 2. So wherever you have z, put this thing. Okay, so your y will be equals to c1 cos 2. What is z? Log 3x plus 2. Okay, and plus c2 sine, the c2 sine 2. What is z? Z is again what? This is log 3x plus 2. Okay, holds this bracket. Fine. Now next, this one. Now next, 1 plus 1 over 27, 1 by 8. Now e power z. Class, can I write this as e power z whole square? So this will be, what is e power z? 3x plus 2. So this will be 3x plus 2 whole square minus 1 by 4. Okay, so this is a final solution for the given Legendre's linear differential equation, this one. Okay, this is all from my side. Thank you very much.